Good morning, folks. My name is Don Corwin from Buell Automatics, and I will be moderating this session. This is part 2 of our CNC workshop, Innovating Both Technologies. This is part 2. If anybody hasn't yet, you should have picked up a handout on the way in. If you don't, they're outside on the table. If you wouldn't mind go grabbing one, you can follow along, and it's also a take-home for you. In review of the session, I did like to make mention that at the end of this session there will be a coffee and pop break out near the registration desk for those interested before we go into lunch. In front of you, we have our evaluation cards passed out for this session. Appreciate it at the end of the session if you do your best to fill them out and leave them in front of where you're sitting. I'll pick them up at the end, and again, we use these for future conferences. The second part of our workshop will feature Ryan Kutz from Aztalan Engineering. Ryan is a machine tool programmer and process engineer with Aztalan Engineering out of Lake Mills, Wisconsin. He entered the precision machining industry at the age of 18 after being inspired by a high school shop instructor and the mentality that comes with growing up in an agricultural background. Ryan continued his education at Gateway Technical College in Elkhorn and Racine, Wisconsin, majoring in mechanical design and metrology. Ryan has worked as a process developer and draftsman and has expertise in CNC Swiss, cam lathes, and has programmed 3-path fixed headstock NC lathes. He has worked for organizations that have served a wide range of industries, including defense, automotive, agricultural, aerospace, and medical. With his wide range of expertise, Ryan has vowed to continue his education within the industry, as well as to offer support to the up-and-coming talent by the way of offering ideas through PMPA's LiftServe, as well as to speak at events such as this. Please welcome Mr. Ryan Kutz.
Thank you, Don. Today's session is going to focus primarily on the innovation that's involved in our industry, and really we don't have to look too far to find a whole lot of that, and I know many of you are aware of that. I'm going to start today's session out by defining innovation and some of the other words that are associated with it. I'm going to provide early examples that transformed our industry, and we'll see more on that. And we'll study the culture as well as pay tribute to some of the past innovators, more well known. At the heart of this session, we're going to do just as it says, explore the art of our craft. What a fitting title. We'll continue by examining the importance that innovation plays on our business, while contrasting this with the unsuccessful, primarily just for fun. We can all learn from our failures, and so I have many to share with you. The building of an innovative culture is interesting. It can go hand in hand with our current culture. It can contradict it in some senses. We'll explore more on that. We'll look at becoming an innovator, an entrepreneur, and the mentality that goes with that. And I hope as a takeaway, each of you begin to start thinking in innovative means and apply that back at your shop. That's the real return on investment from these sessions, and I hope that you can take something with you today. So, as Don concluded, I come from an agricultural background. My father is a grain farmer. Machining was new to me, but it was something I wanted to pursue and was passionate about. So in that respect, bear with me here, and I'll try to give away the farm. So we start out, what is innovation? Well, we can look at its definition. A new idea, device, or process. And you say, no, that's an invention. And you're correct. And so let me add this. Innovation is the act of applying better solutions. Sure it is, and it's in that act that you find ones that fail and others that succeed. We look for a truly effective solution, an effective product or process, and that can be many things. It could just be small improvements on our machine tools, or it can be a whole new process, a whole new design, perhaps a whole new machine tool or cutting tool, what have you. So it's true, innovation differs from invention in that innovation refers to the use of a better product or process, where invention focuses on the act of applying that process. I give this example, the turret lathe. How many of you own a turret lathe? Good handful of you. The development of the turret lathe, and we can read this, the middle of the 19th century, they say was a key aspect to the advancement of manufacturing. That's a pretty profound statement. I think we can back that up though. Take a look at it. See, you ask yourself, well, how was that effective? What does that do for my bottom line, right? Well, unlike bench lathes and the engine lathes of the time, it provided us automation when changing tools. Prior to this, a tool change required a machine setup. The operator would remove the tool, install a new tool, and so he'd judge it by dial and feed the tool on his bench lathe. Okay, it also provided repeatability, didn't it? We had adjustment screws on them, and as you would actuate the lever of the turret, it would come to a dead stop, and you could adjust that per position. So another innovation. I'd also add that it made it possible to operate with less skilled labor. No longer you needed a craftsman, but rather just someone to actuate that and run it against the stop. Okay, and we look at the evolution. Recall what Bruce told us at lunch the other day, that it starts with a new idea, a new thought, right? And innovation is the act of applying that thought, like we just learned. And it's fun to look back at the turret. It started with the concept of the indexing cam, right? The mechanism behind it. And so from there we could build a prototype and see, yes, it truly does index. It does what it was intended to do. And from there we could apply it to an industry, namely our industry, precision machining. And that's not the only one. You may find a turret on, say, a Army tank, same technology. But it was studied and it was found effective, right? The setup times were reduced, the skilled labor burden was reduced, and so it fit the industry well. And today we look at what our current turrets look like. We could run through the list here. They're adapted for numerical control, the use of a stepper motor, all new. Logic dictated the turret angles and the positioning of it. The hydraulics can clamp that position in place. The sensors ensure that its position has been met. They're driven for live tools, geared for live tools, driven tools. Plumbed for pressure, coolant pressure, high pressure. Sure. Simultaneous heads, as you see here in the lower left. My lower left, you're right. Simultaneous heads, we can increase productivity with the use of those. Also add capability to our machine tools. And I mean it was a total effective solution, and that's what we need to focus on. But recall that it started with one idea and what it's become. I have an animation for you here. Here we see the turret in full operation and all the systems involved in that. Oh, shows up on mine. I apologize. I don't know what happened there. So, non-effective solutions. These are fun to look at. In the background, you see the flying tank. And before military planes were robust enough to carry a tank, the military bigwigs got the idea, well, let's put the wings on the tank and we can fly it right into the battle zone. Original testing actually proved effective. They did get the tank off the ground. They towed it up. But where it fell short, on the ground. Not a very maneuverable vehicle, certainly a big target. And so a non-effective solution, and hence you don't see any flying tanks today. At least I hope you don't. Another one, the mono wheel. Some innovators thought, well, most of us travel now on either 2 or 4 wheels, wouldn't it be cool to travel on one? and we see some of that, but obviously not mainstream. Safety precautions, probably not a real good ride, and so was a non-effective solution, and I would doubt if anyone rode their mono wheel here, but I certainly didn't. The vacuum beauty helmet, and while one gal looks evil and the other one looks scared, this isn't a crime taking place. Back in the beginnings of medical devices, we can find all kinds of examples like this of non-effective solutions. They did know how to do one thing though, they could market it, and they sold many of them, but they forgot one key design aspect here, and that's that I call her victim. She needs to breathe, right? We can't breathe in a vacuum with a plastic bag over our head, certainly. Another one that you'll see, the scooter-mounted cannon was a product of the French post-war. They didn't have the ability the cash flow to keep up with some of the modern amenities in warfare, so they improvised. And don't assume that that provisions will lead you to non-effective solutions. I think improvising is something that we all do, and our industry certainly is compromises, right? We compromise one thing for another continually, day to day. So know that, but we still have Vespas, we still have M20s. They just don't go together real well. And same thing here. It couldn't take what it was dishing out. So a non-effective solution. But you say, well, who's behind all this madness, right? And certainly the innovator is, and we can define that. The innovator is a person, one of the first to introduce something new into reality that's better than before, right? It's just an improvement. It can be an improvement. It can be a new device, but the innovator is the person that got it done first. And I'll add this, that it opens up an area for others, right? And so achieves an innovation. And we can look at, let me jump back here. Let's take a look at some of these guys here. You'll see, starting on your left, Isaac Newton, certainly an innovator, pioneered classical mathematics for us, had many breakthroughs there. Albert Einstein gave us special and general theories of relativity, and man, the work that was involved in that, I can't imagine. The Wright brothers, residents of Ohio, Dayton, Ohio, Orville and Wilbur gave us controlled flight, in powered flight in a heavier than air vehicle. Right? Thomas Edison, what'd he give us? Gave us a light bulb, right? A use for our electricity, and certainly he knew how to create a customer. Nikola Tesla, be sure to thank him. You don't have any overhead belts in your shop anymore. Dennis Ritchie, maybe not so well known, but gave us the Unix operating system and C programming language. And isn't it marvelous what the computer has done for our industry now? How many of you own a computer? More than turret lays, obviously. Henry Ford, our last, obviously well known, gave us mass production of the automobile, and we knew his take on customer requirements, don't we? Give it to him in one color, black, and you probably never have a quality issue when it comes to getting the wrong color. But the important part here is that we understand, we humanize these people and understand who they were before they were innovators. Certainly we know them all now, but who were they before that time? Well, Isaac Newton had said that he was born to farmers too, and while I don't know how true that history is, like a horoscope, it's probably a good guess. Most of the population then was, and look at how that industry's changed. Isn't that magnificent? 1% of our population feeds most all of us. Albert Einstein, born to an engineer and a salesman, and Hermann Einstein. He after graduation, took a job at the Federal Patent Office in Switzerland, and certainly surrounded himself with new ideas, right? At the forefront of breakthrough, he was seeing this, and that's something we can consider, can't we? Is two parts. intrinsic brilliance and acquired knowledge and how they go hand in hand. And as we talk about some of these folks, let's think that, let's understand that. Where did they get the knowledge? Was it acquired, or were they just, was it intrinsic brilliance on them, perhaps inherited? The Wright brothers had opened their cycle shop in Dayton, Ohio. Bicycles. Certainly doesn't have much to do with aircraft, does it? It wasn't until the death of a famous aeronautical engineer, 1896, that inspired them, moved them to become passionate and take an initiative to experiment with gliders, and later on powered flight. Nikola Tesla, you probably didn't know this. His mother invented small mechanical household appliances and home-crafted tools. And when he took his job at the Central Telephone Agency in Budapest, he had an idea there in Hungary of the induction motor. And when they asked him where he inherited his creative abilities, he cited his mother as a source of that. Henry Ford, another one, born on a family farm. He was 13 years old when his father gifted him a pocket watch, and the young lad, he continued to disassemble and reassemble it, and maybe we could use that for some of our new hires, couldn't we? Sit them down, here you go. But anyways, he took a job as a machinist in Detroit to support his family, and here he learned the skillful operation of steam engines, how to rebuild those. And certainly that inspired him. It wasn't until later on he had to return to the farm briefly in support of his wife and his family. He was married then, and later on took a job at the Edison Illumination Company. And it was there that he started his plans for the first Ford quadricycle. I believe that 1888 is when that started to develop. His talents there promoted him to chief engineer. And like I say, while he was there, he developed these plans, and that's interesting to me. Here he is a senior engineer at a company thinking entrepreneurial. He's going to go on and create his own business, and what was it there in the culture of the Edison Illuminating Company that allowed for that? And we can explore that a little later. Perhaps maybe they saw potential new business in the horseless carriage, its requirement for headlamps. I don't know, or maybe they just weren't worried about the productivity of their senior engineer. I don't know what it was. But so we've humanized these people, right? They came from humble beginnings. Many of us have too, and look at what they've become. It was that new idea, that new act they acted on. Thank you, Bruce, for mentioning that at lunch, but that's really what it takes. It takes an initiative on that new idea to have a breakthrough innovation, and it comes with a lot of hard work as well. But we've heard this, right? We've heard hire for potential and train for skills, and certainly we can see some of that. So you ask yourself then, what potential, what attributes should I be looking for if I were to pursue an innovator in my company? And I can share some with you. The qualities of a good innovator challenges the status quo. They're dissatisfied with their current reality, right? And we saw that in many of the examples I just provided. They question authority and routine. They confront assumptions. Certainly they do. And so we can judge their curiosity, and maybe we can do this with our new hires as well, is take them out into the shop, see their curiosity, see what they cling to. A good innovator actively explores their environment. They investigate new possibilities and honor their sense of wonder and awe. They're certainly self-motivated, and that's a good quality in any of us. They proactively seek new jobs, but they're also intrinsically rewarded for their efforts. They're visionaries. They think mental pictures, and we see that in our industry. How many of you took a 2D print and envisioned in your head what it looked like as a 3D model, right? And of course, today's software allows for us to do that, but well, we had orthographically drawn prints still come across our desk. And so we can be that visionary. We can maybe look into the future, see where the industry is headed, come up with a new idea to aid that and pursue it. They entertain the fantastic, and you could say that they conjure up the impossible, outrageous scenarios. And certainly we saw some of that in the non-effective solutions, right? But they made one step that a lot of us hadn't. They tried it. They wanted to see if it worked, right? And to Greg's point there, don't go the path of no way. Try it. They take risks. They go beyond their comfort zone. They're experimental and okay with the non-conforming. You could even say they are courageously willing to fail, and we can learn from our failures, certainly. I'm reminded of a gentleman I met earlier on in my career. He told me, he says, Ryan, he says, I've failed more times than you've attempted. And it was a true statement he had. And he had learned from those failures, and that was an important lesson to him. He didn't want to repeat them. Some of them were more painful than others. But he had that was his acquired knowledge. He knew what worked, what didn't work, and took that on with the rest of his life. They're peripatetic. You say, what's that? Well, they can change work environments as needed, right? They wander, they walk. We do some of that. Anyone that sat in front of a computer programming CNC machines certainly has to get up and walk away, put a fresh set of eyes on it. We all need a fresh set of eyes. We can enjoy that, or even a second set of eyes. Humor and brilliance play a role here, right? They appreciate the incongruencies that we encounter. They're self-accepting. They make new connections. They can recognize patterns. Certainly we see that, right? Who's sorted parts in their life and had to look for that non-conforming piece. And they tolerate the uncertainty. That's very important. A lot of our business is evolved around certainty, and the innovator strives in times of uncertainty. Another topic we'll discuss. Committed to learning. Obviously all of you are, and you're here today. So congratulations there. Continuing your education is very important, especially in this industry with these new advancements basically daily. Greg touched on the carbide tools. I mean, who would have imagined 20 years ago that you could run something 18 thousandths a rev? Certainly not me. They're preserving, they're resilient, persevering, flexible, and adaptive. And while all this is important, it's certainly not everything. They need that culture, don't they? And we can adopt that company-wide culture. Well, let's explore here. I intentionally left some words out when I defined the innovator, and you'll see it here. It says the innovator was the first person who introduced something into reality, something better than was before. And I'll add the words there, or organization. And typically that's what we would see today. Not one person, but a team, a committee, a crew in your shop can come up with new ideas, get everyone involved, obviously. So you ask yourself, well, it's starting to sound like continuous improvement, and it is. But the two don't necessarily go hand in hand in their full respect. Continuous improvement is a business philosophy, and as well as lean. And most of you have probably adopted that right now, and we can find that in your quality policy. But let's take it another step further. There's continuous improvement, discontinuous improvement, continuous innovation, and discontinuative innovation. And we can explore those a little bit more. A series of small wins, though. A series of small wins. We can see that on our machine tools, can't we? A new process, a new method, a new way to go about it, a new chip former, curler, a new coating, whatever it be. You start to add these small wins up, and all of a sudden you've got large change, don't you? And you can see by just going back in history and looking at what some of us did, earlier on. But the point being, a series of small wins is the momentum needed to drive that large-scale change, and we can adopt that philosophy. Continuous improvement works best for firms that are trying to play catch-up. They know the direction they need to head by observing those around them, right? And so we can make those improvements because we've learned them, we've gained them as acquired knowledge. I'll add this, that When firms are operating on the frontier of technology, more discontinuous innovation is required. It's small wins, it's small changes, it's that new device and the small steps required in developing that to take it one step further continually or non-continually. Sometimes it's just a new device, here it is, populate the market, right? Innovation is best associated with creative solutions, and these can occur at small as well as large scale. So you ask yourself then, well, I've got a culture already, Ryan, and we've adopted lean, and so my question then is, well, can innovation culture and lean culture coexist? As certainly they can. At one time, the Toyota system was known as one word, right? Lean. And it became a fad, a mantra, and that transformed a whole lot of companies. I'm here to say that innovation hasn't had that fad or mantra, and I would also add that it's not needed. The competitive marketplace drives innovation. It's about being better, standing aside from the crowd, making that new breakthrough. And then that's what can set you apart from your competition. So am I saying that lean and innovation can't coexist? No, they certainly can. And I'll add that lean can provide the framework for innovation. And what I mean by that, the lean concepts, right, because of what they're required to do, right, reduce waste, we can use that as innovation, or we can use that in developing our innovation, our new process, our new product, the same. The experts at the Boston Consulting Group added this: lean and innovation can indeed complement each other, and they say it's about time they came together. Lean brings a structure and predictability to innovation and sharpens the distinction between idea generation and development process. Both share a common goal to meet requirements, customer requirements. We know all about that. And I'd add that they both fail in the same way by focusing on the tools, right, and not the philosophy or the people involved. So I have this cartoon that really sums it up well when we start to talk about culture and management. The teacher stands at the front of the class and he tells them, well, I'm here, I expect you all to be independent innovators, critical thinkers, and do exactly as I say. Well, what a contradiction, huh? And don't we get the same mentality sometimes from our management? So about management, when do we need managers, right? During the growth phase, certainly. We need to hire managers who can excel at planning, analyzing, and optimizing. And these are the skills that they were taught. So we ask yourself, what skills weren't they taught then, right? Well, they weren't taught how to create a customer, and consequently they can't optimize or they can execute on existing businesses, but they don't have the skill sets necessarily required to provide innovation for new products and new services, right? Forbes notes this: 50 of 526 companies they surveyed were able to reinvigorate their innovation. And this shows that it's rare, certainly, but it can be done. And as Bruce told us, the time's now. And that's my apologetics to no fad, no mantra with innovation. So of those surveyed, what techniques were employed? Well, certainly insight, questioning, observing, experimenting, networking. Discovery, they knew the job to be done, their management. In lean, we call this Gemba, the Gemba walk down to the floor to see what the problem is, right? Discover the job, discover the issue. They found solutions, they found problem solvers. They found problem solvers that were capable of finding the root cause. And so to their solutions for those problems, they built prototypes. I like to add one thing: build minimal prototypes, keep it simple. Here's one that's not. The ball valve just operates as a simple ball valve for an anesthetic machine, but the engineers got a little carried away for this, and all of a sudden it wasn't very manufacturable anymore. That certainly didn't do a good job for them. So our conclusion here: managers will need to learn a new set of skills, right? And here you can see them. I forgot business model, I add that. You need to know how to market these solutions. A lot of time the innovator isn't the person that would market these solutions. Sometimes they are, but a lot of times you'll find that that doesn't work real well. But they certainly know what it's about and need to convey that information on. But our conclusion here is that managers need to learn a new skill set of management. They need entrepreneurial management, the principles used in effective startups, business startups, rather than traditional management. Traditional management works well in relative certainty. The innovative approach teaches how to create value, while the traditional management captures value, doesn't it, and scales business as appropriate. So I have some examples of innovative cultures. The Sandvik Productivity Center is certainly one. Look what they've done. Brought the machine tools into their facilities in order that they ran their tooling. While doing this, they provided a service to their customers as well as an ability to market their solutions. Another one here, the University of Whitewater, Wisconsin, my hometown. It took the whole community to build this, but the Innovation Center and the UW School of Business there in Whitewater had identified this problem with producing management internally, and that they didn't have this innovative thinking, right, these skills. So they developed the Innovation Center and so changed their curriculum. But what the Innovation Center does is it provides square footage for those that are ready to go into business startup, the entrepreneurs coming out of the UW business system. And that's all essentially it is. If you have a new idea, that's the place to go. And I would assume that these start to pop up more and more. I've certainly seen a lot of them in my state. But there again, they provide the market research needed that maybe the innovator, the guy with the new idea, doesn't know how to do, and help foster innovation and grow it. And the idea there was that if we do it within our community, chances are a handful of these new startups are going to stay, and hopefully they'll stay in our community. So, all right, now that we've muddled through all the dry stuff here, I want to do a fun little thing. I want you to think of your favorite sport and think of some of the innovations that have become of that. And to get you started, maybe you think baseball, right? And the baseball mitt, look at what that's done for the sport. It was certainly a safety item, right? And kept the catcher's hand from hurting. It was also an effective solution. It allowed you to catch the ball easily, right? So think of that. Think of your favorite sport and all the innovations that have come with that. And I'd like to share my favorite sport, tractor pulling. Again, coming from the agricultural background. And it started with an idea, right? An idea for competition. See who's got the strongest horse, I guess. And later on, the steam engine. See who's got the most power in their steam engine. And so these markets develop, both the agricultural and automotive. And some guy got the idea, well, I can take my V8 out of my Ford and put it in my tractor, and it seems to be a lot more effective for me. And so a new sport was born out of pretty humble beginnings. And later on, my father said, well, that's real nice. I like your V8 tractor there. But I'm a war veteran, and all I know is Huey helicopters. And so he took a T-53 Lycoming engine, 1,100 horsepower, and put it on his tractor and went down to the county fair here in Ohio. Spent a lot of time, popular sport here in the state, and it was an effective solution. I'm proud to say he went on to win the national title shortly after, but wouldn't hold a candle to the guys today. And just to reinsure that, look at how far they've come. 6 engines, 2,500 horsepower per engine, 15,000 horsepower on one ride. How'd you like to sit on that thing, huh? Forced induction really took the turbine out of it. The piston engines were good at providing torque, and that's what the sport is all about. Much horsepower in the world, if you don't have the torque behind it, you're not turning the tires. And so you see it there, the use of the supercharger and turbochargers to move air and fuel into these vehicles outweighed the low torque of the turbine engine, and so we don't see them anymore. You say, well, that's great. Well, what does this have to do with our industry, right? And it's important that we understand the sources of innovation. Innovation can occur as a result of a focused effort, either by chance or by failure, right? The unexpected, incongruencies, process needs, industries and market structure, changing demographics, changes in perception, or new knowledge all can lead their way into innovation. So I have an example for you here. This was a focused effort of ours. You may have saw one sitting on the table on your way in. Flightings, new product for us. Machine flightings for the food industry. And so this is how they convey their food in their machines. They had a whole stringent list of requirements for us. 16 RA surface finish. We didn't want any voids to capture bacteria, and so it had to be polished. But we had a problem. The pitch on the thread to single point exceeded the maximum rapid traverse of the machine. So to get to any decent surface footage, we certainly couldn't move fast enough. And maybe this one isn't the best example, but some of them had a pitch of better than 2 inches on them. The next question is how do we deal with the length? These things are in the range of 1/4 inch diameter to 4 inch diameter, from 4 inches long to 52 inches long. And they looked to us to source this entire list of products. They wanted one vendor and wanted to go to them and say, okay, I need 5 of these, I need 2 of those, I need 3 of these, and how can you accommodate me? And we thought long and hard about it and came up with some solutions. But they wanted no mismatch in the tool marks again for the surface finish, and so we couldn't re-enter the cut, and that really posed a problem for us. Another thing, we were working with unfamiliar processes. We weren't quite sure how to process this, but we were focused. And you say, what were we focused on? Well, most of us were focused on 80 to 85% profit margins, the ability to have that. Certainly we don't see that in a lot of our commodity parts. It was a new customer, it was new potential business, and it diversified our market, and that was a big problem for us. We had all of our eggs in one basket at the time and turned to prototyping to try to diversify. So we needed creative process solution, and we found that in turn milling, radial turn milling, something that was certainly new to us. But this allowed to solve a couple of the customer requirements. It provided us the continuous cutting motion we needed. It slowed down the workpiece spindle, right? Because now the SFM was in the RPM of the mill, not in the RPM of the spindle. Certainly we climb milled to reduce the deflection there and provide us with our finish. The Z-axis feed was no longer a problem. We weren't exceeding the maximum rapid traverse, certainly not. And the C-axis, the rotation of the work spindle, and the Z were just tied together as points. But we knew that pinch milling could increase the stability, but we had a problem. We didn't have a y-axis on any of our mills. We had an upper y-axis, but no lower, so we couldn't pinch mill. And so we thought, well, how are we going to how can we build rigidity into this process? We didn't have a lot of good answers up front, but it took some critical thinking. We knew one thing. We knew the Swiss guide bushing and sliding headstock allowed for long length to diameter ratios. Certainly it does. We see that in a lot of our Swiss products, true Swiss products. But we asked ourselves, well, can we adapt that mentality, that device, to our current fixed headstock machines? And the reason we needed to do that, again, some of these parts were 4 inches in diameter, certainly bigger than any Swiss machine I've seen that could deal with that kind of length. And so I went to the boss and said, well, I have an idea, right? We'll just build another set of rails behind the headstock we have and put our servo drives on it, and it's only $200,000. Wrap it up in the sheet metal and you've got your machine. Certainly ROI needed to come into play here sooner or later, and this wasn't going to justify a custom machine tool. So we recalled, well, we have a W-axis, the motion of the subspindle coming up to transfer the part, right? And we thought, well, that's interesting. Could we keep the bar static and move the subspindle with a free sliding fit along that static bar, in turn providing the rigidity we needed. It could just follow the mill up and down the length of the bar. And so we gave it a trot. We ran into a lot of issues there as well. You see, I don't know if this will show up here now. No. Nope. I apologize here. I had some videos to show you. Let me back out of here. It's important that we see this example. Yeah, I guess we're not going to get it. I apologize again. Anyways, as I explained, we just traversed the W-axis. What we did is we bored our own subspindle using the ring on a quick change collet. We used that ring then to set the fit. We bored the collet a few tenths oversize and allowed it to slide freely up and down. Of course, we can monitor the servo loads while we did that. We could watch just how good of a fit we had. But it essentially followed the tool. But we ran into another problem, is that when you feed in a C-axis, you have to take into account the circumference of the diameter you're working with, certainly. And we needed to keep the sub-spindle and the mill tool in sync. Well, the sub-spindle was moving in a linear fashion while the other tool moved in a centrifugal fashion, right? And so we had to account for that, and we were able to do that through our programming and a series of weight codes on each position and so on. As you say, wow, that must have taken a lot of programming. Certainly it did. Here we can see all the variations in the chart below of this part. All low volume, high variety work. Certainly a task to overcome. And so we used our macro programming ability to deal with some of these variables. The customer was kind enough to spell them all out for us in this chart. All we had to do is apply them, right, to our program language, and we could do that. I had another video here to show you, but I can't. And here we can see some of the programming. So the first two columns are main spindle, sub-spindle, path 1, path 2, right? And they go on for pages and pages and pages and pages. What we had to do was surface. We didn't have a y-axis, so we stepped down incrementally in X and adjusted our Y and Z positioning accordingly to surface the rake angle on the side here to provide them with the walls that they were after. And the code went on and on and on. And so we looked to macro programming and a repetitive statement on the right-hand side, and there you have the whole program within that little bit. And certainly that wasn't all of it. We needed to accommodate a lot of other variables and have worked towards that. So here's some more on innovative programming. We use an Okuma lathe, what have you, but the Okuma provides us an open interface, and so we can ask the machine tool controller what its condition, what is the condition of any portion of this machine, right? Is the oil on? Is the oil off? Is block delete on? Is it off? And so we can pokey yoke and avert crashes rather than relying on the operator to know all the conditions that the machine tool has to be set in prior to operation. We just simply ask the machine tool, and if it doesn't meet its condition, it stops. There's some other innovative programming you can do with macro. Scaling, sizes, floating positions. Certainly that's pretty straightforward. Scaling is multiplication and division, and floating positions along an axis is just addition and subtraction. We did some letter engraving. Now that we could float and scale them, we picked the font that we liked and stuck with that, and produced code for each letter in a series of codes that you could essentially just call the letters in whatever order you needed them to be, scale them appropriate, and float them amongst the machine. We added adjustability, finer adjustability, again through multiplication or division. We could also give infinite adjustability over time. For those of the FANUC guys, you see that in G10. We variable speeds and feeds there again, like I talked about, the W-axis and the C-axis needing to feed together obviously was just a function of division. And repetitive processes, we see that, can cycles, multiple parts per chuck, whatever it needs to be. But really that's what's driven some of the latest advancements in conversational programming, a new method. So innovations resulting from failure. And the first one that came to my mind was stainless steel. A gentleman early on was experimenting with steel chemistries in order that he found a gun barrel that didn't erode from the bullet traveling through it. And he continued to fail, and eventually he walked out to the scrap pile and took a look at his failed gun barrels and found that a couple of them didn't have any surface rust on them. And so developed an understanding for the effects of chromium. And we can look at failure. There's all kinds of failures in our industry, in our machine tools. I have some of them charted here, the different devices and how they fail, bearings, seals, right? All this stuff. And perhaps you can find a new innovation or a new method within some failure that we already have encountered. I'll touch on automation for a little bit. We've talked a little bit on automation. Automation is the opposite in a sense that it automatically stops a machine without human intervention when some condition or variable is unsatisfied symptom. What can this do for you then, right? Well, it can prevent contamination, right? Cross-contamination of conforming product off the machine and then that non-conforming piece that floats in there. And so we can avoid having to sort, having to rework. But one thing to keep in mind if you're going to build an automation device, consider it failing as well. And what happens when it fails. You want it to fail. You want the machine to stop when it fails, if it were to fail. You don't want the machine to continue running without the device recognizing that it failed. And so I have an example of this. I was employed at Precision Plus for a good long number of years. They used Tornos cam machines, and they had retrofitted them with a bar loader for high production jobs. But we had a problem, a failure. In this case, it was just a broken tap. And the customer couldn't deal with this. They couldn't tolerate no threads in their part. And that was because their systems were automated, and the automation didn't have a brain, in a sense, and wasn't able to catch this part with no thread in it. So we needed to come up with some device, some way of stopping this machine on the condition of having a broken tap. And we were able to do so. But, the customer was a plastic injection molder, and while we just made little 10-cent parts for them, it became a bigger problem the farther downstream it went. They continued to assemble these threaded inserts into their plastic injection molds, and they weren't necessarily found until after the mold was settled. And here some guy came around, oh, there's no threads in it, and the whole mold was garbage. So it was a painful problem for us. But how does one avoid a broken tap, and what exactly is the root cause? And you can say, well, speeds and feeds, Ryan, could have been optimized to keep that tap from breaking. Perhaps you could have opened the ID up a little bit bigger and less thread percentage and avoided breaking there. But what it boiled down to is that we didn't have the systems to catch this. And we continued to try, but every time we ran these parts, we ended up with a rejection, and we would sort, and we would sort and sort and sort. And quite frankly, we're sick of that. So we came up with this method. Here you see the end working attachment of the Tornos screw machine, and I'll point the steel braided line coming in is just to a proximity sensor looking at the trip dog on the tapping clutch. The old timers knew that if the clutch was still running, the tap was broken. It hadn't tripped the clutch and shut the clutch off. And I said, well, I've got a means to monitor that fairly easy. And for the price of about a $200 sensor, we were able to get it done. You'll see here some of the logic involved. Obviously, This machine runs on mechanisms, on cams, right? And doesn't have any logic like our new amenities as our CNC machines do. So it wasn't as simple as plugging the device into a spare M code. We had to build an emergency stop. Some of that legwork there was done when they retrofitted for the bar loaders, but just built a secondary emergency stop essentially, that when this device didn't find its position, it would stop. Hey, look at some of the sensor technology today that's on the market. I have some examples here from SPC Innovations. Just a needle that's pneumatically controlled, and it's going to whip over and touch the tool. And if it finds that the tool isn't present, same thing, you get automation. We stop the machine, right? There's all kinds of different variations of these things. We can fit them in just about any machine tool. And they're pretty simple. If you have the logic already built, these come with them. They're fairly cheap. And it's a good means to avoid that potential problem with your customers. But our logic didn't work quite the way that those do, and perhaps we could have used one of those. I'm not sure if they were on the market at the time or not, but we had our device. And so we looked at the cam, and the tick marks on the cam were picked up by a photo eye. These markings were there already, and we just essentially counted them to know where we were at in the process, to ask whether the tapping clutch was engaged or disengaged. And what it boiled down to was a $60 PLC off Automation Direct, about $200 worth of sensors, and a whole lot of time. But it was effective. It was an effective solution. As far as I know, they haven't made a part without a thread in it, because what it did is it stopped the machine prior to the cutoff, so the non-conforming part was still attached to the bar. Here you can see some more. At one time we had also looked to monitor the drills, thinking, oh, if the drill breaks, the tap certainly will, but that begs the question, well, why do we need to look at the drill if we're already monitoring the tap and it's a consecutive operation? Here you see the automation device to pull the clutch. That was our shutoff. We found that if we just killed the power to the machine, well, it just slowly crept down to a standstill, and in the midst of doing so, it continued to break all of our tooling. So pull the clutch first, then power it down. Here we see some of the logic. Our PLC used ladder logic as a programming method, right? But ladder logic was originally invented just as a way to document relays, right? The logic that these relays have. And the reason we chose the PLC, it was more absolutely than what we needed, but it allowed us the ability to expand if we needed to add more devices in. Like I say, for $60 you can get a PLC that has 18 inputs and outputs on it. Some of these Ice Cube relays are upwards of $150 and only do one operation. Or maybe two or three, but that would be about it. So we can see the logic here. It's just a series of on-off switches. If the cam's in the right position, it's on. And so if that cam position sensor is on, let's take a look at the prox sensor on the trip dog, right? Monitor that condition. And if the trip dog also finds to be in the incorrect position, then stop the machine. And so we added some more. We had another problem. When the bar loader loaded a new bar, it wasn't always accurate in finding the front of the bar, and so we could end up with a non-conforming piece, our first piece off. So we used a solenoid valve and some air blow to just blow it away. And that was operated off of a signal from the bar loader, new bar signal, just one output. We had to use a relay because we didn't want to sync power sources into opposite devices, so that the relay is what transferred that bar signal into the PLC. The PLC told the solenoid switch, blow air for 5 seconds, whatever it took to operate that first part, and so that part fell in the chips rather than going into the pickup tube. Here's some other things we can consider. Devices we had on our Tornos. The spindle stop. This is available on quite a few machines, but here again the goal is to avoid secondary operations, and so we can stop the spindle with this device and do cross drilling, face milling, off-center drilling, whatever it be. So how does it work? All right, well, it's a pneumatically operated system, and it actually is the logic is a cam, and I suppose that's probably the best way to go about it. If you're a cam machinist, you're familiar with this. But the cam hit a micro switch. The micro switch pulled the power away from the original drive unit, and so applied the brakes and stopped the spindle, and then reversed its operation to fire the spindle back up. And I'd like to thank Al Smith at Future Swiss for providing some of these examples for me. They've pioneered some of this knowledge. So the spindle stopped, but we didn't have C-axis control, and certainly we couldn't do this by a cam, but with a little bit of logic, we can provide indexing, clockwise, counterclockwise direction, so maybe, I don't know, left-hand drills are getting hard to find, it seems, higher quality at least, and so now we can go clockwise instead of counterclockwise with the Tornos. Eliminate the need for secondary operations. It could provide, I believe, up to 12 indexing positions, as well as spin both directions. Here they are. And so it was programmable, right? It was a cross of two technologies, the CNC technologies and the CAM technologies, and so it was a retrofit. Programmable, but it interfaced through this RS-232 port, pretty common cabling, and so it came with the logic and so on. And with that in mind, now that we're stopping the spindle and have C-axis, we can retrofit some of these high-speed spindles on for the efficiencies. But also typically the CAM machines are smaller machines, so we need higher RPM to achieve the surface footage on smaller tools. Some of these are capable of doing 120,000 RPM. And we could look at innovative mounting solutions for these. I'll share a couple with you. Down in the bottom you see some different holders and slides. In the background there is a rotary coupling that's used to transfer the air needed to or the electricity needed to drive these live spindles on a turret. This way we don't have to take precautions into which way the turret indexes continually. We just let it spin. The one in the upper corner there is actually for a mill, a vertical mill or horizontal mill with a tool changer on it, and it feeds off the live air next to the spindle. And so you see that it's standard taper, pick it out of the tool magazine, plug it in, and it's driven by the air of the machine tool. It's about as plug and play as it gets. So we look at automation, right? We can define that. Automatic control is the use of various control systems for operating equipment with minimal or reduced human intervention. That's all it is. The purpose here, to save labor, energy, and materials, or to improve quality, accuracy, or precision. We pull that away from human repetitiveness, right? Any repetitive job, certainly you should be considering automation. We could find some of this at our company, Aztalan. You'll see above. But know that it started there, right? With the automatic lathe, we had automation, multiple tools at one time, and so a humble beginning. But you look at some of the other stuff we've done, automatic palletizing, part loading. Here you see this machine down in the corner is capable of holding 10 tombstones at one time and changing them in and out of our horizontal mill, and has provided the efficiencies for us on some of these long-running legacy parts. Again, less need for an operator. Take a look at robotics. What can those be used for, right? The machine tending, palletizing, auto loading, logistics, inspection, deburring, cleaning, welding, assembly, painting, and packaging, just about anything. And there is somewhat of a misconception with robotics, but that maybe they're not flexible enough for our shops, right? How does a job shop justify that return on investment for these new devices? Well, I'm here to say that is a misconception, and they have become very flexible. They're capable of interacting with people now because of load monitoring systems and such. You can essentially just run right into the arm and it will stop with little to no force. because it knows the job to be done, and it knows if it senses more load than what it should have had, it can stop. So here's some pros and cons, right? We talked about flexibility. Integration's another one. We need to integrate these to talk to our machine tools, and of course we end up with, whose problem is it? But they are becoming easier to use. Certainly the programming's been simplified. We can essentially just use a series of joysticks to walk them into a position, save that position, capture the motion it made to get to that position, and it can essentially be as simple as that, this point, that point, and so you teach it the job to be done. I'd say automation and lean misconceptions, that maybe automation and lean don't go hand in hand. That's interesting, isn't it? But give the example of the conveyor. And isn't conveyance as lean viewed as waste sometimes, but maybe a necessity? Just another good option. If you're conveying a lot of product, if you have a lot of logistics in your business, perhaps you consider some conveyors. Also innovating for efficiency. And here we can look at some different attachments. I have one here. It's a milling attachment, spins with the part, allows for no spindle stop, no need to stop the spindle. Planetary gears will drive that motion, and so you can saw, you can mill, you could stack them up, stack the mills however you'd like in this, and like I say, no need to stop the spindle, adds efficiency, right? There's multiple other ones we could find. Perhaps it's drilling 2 holes at one time, drilling 4 holes at one time, and you could see the same deal here. We're just using some displacement in there to actually feed the drills in and out. So thank you to the folks again, SPC Solutions, and if you want more information on their innovations, be sure to visit their booth. Safety innovations. Here's another interesting one. Keyence gave us this technology to minimize the cages needed around our automation. We'd just send a light curtain down, and at any time if something breaks that light curtain, we'll stop the automation device. And so it was safety. I will add here too that if you need to encounter some obstacle that moves, perhaps parts come down a conveyor and could interfere with this light curtain or something, it is capable. It does 270 degrees, fans out in an array as such, and is programmable to eliminate certain positions from that detection. We can innovate for process monitoring, can't we? I look at all the different devices here. We can check the size of a feature with devices such as this, right? Take a diametral reading within the machine. That's where the heart of quality really is, at the machine tool, right? That's why we call it assurance. We can take length readings, right, in the same fashion, and the logic that comes with those. Here's just another one in a different position. The other one was the right angle. This is straight on. But basically, you run it past the end of the tool, it displaces the sensor to a certain degree and can act as the I/O switch. Can also provide you readings back in analog. But look at all the other ones too. Vibration, strain, deformation, temperature, there's an interesting one. Forces, acceleration, acoustics, and power consumption. All things that we can monitor to understand exactly what our processes are doing, and all of them being devices that can work as automation. Here's some other ones. We could check the coolant level, can't we? In concentration, pH monitoring of our coolant. Okuma's pioneered some of this. Actually can get it right to your smartphone now. As a machine tool, and I would suggest, well, if all you're after is level, maybe just go down to the hardware store, get a float valve and a caution light, and when that float valve comes up like it does in your toilet, it turns the caution light on, and so you know that the screens are plugged somewhere and the coolant level is too high and perhaps spilling out of the machine. A pretty simple way of accommodating that, and so we don't need the operator to go check coolant levels every so often. The machine alert system, another one, like I said, capable of sending machine alarms right to your smartphone, right to your desk, right to the boss's desk, whatever it needs to be, to alert that operator. Perhaps you have good enough process capability that the operator doesn't need to babysit the machine, and so, or you run lights out. And in doing so, here now is a means to provide that operator with the exact timing of when he needs to go attend it. Perhaps it throws an alarm or is programmed to do just such after so many consecutive parts or offsets. Another interesting innovation here is the RFID technology, radio frequency ID, for tool management. It's interesting, isn't it? We can run the tools in our tool changer past a radio frequency scanner and assign each tool a different frequency, and so we can monitor in-cut time, monitor the use of some of our tools. I know we have this problem at Aztalan. Some of our horizontal mills are capable of holding 75 tools. And it's hard, it's challenging to keep track of all those. What's in there? What exactly do you have in there? And which ones are used more than others? Maybe something makes sense. Maybe we need to lose one, gain another. So I talked a little bit about crossing paths, right? Different technologies and how they cross paths, and we call that innovation in some sense. So here's some devices that you may encounter. Different things used, motion transfer, sensor technology, relays, the logic, the PLCs, conveyors, all this stuff could show up. Certainly all the sensors, and to me the sensor technology is the new wave of the future. Rather than relying on an operator to determine the status, the symptoms of any machine, we can simply just do it with a computer and analyze the data and achieve the results that we're looking for. Here's kind of a fun one. Say homegrown innovation that utilizes waste, and I provide some examples here. The workbench just needed some better lighting. It was fluorescent lights we had in our shop, and so we built a structure up around it and put the lights up where we needed them to be. We do some spindle liners just out of standard tubing. Welded a flange on, and so we could bolt them in and accommodate all different kinds of sizes of materials in our 2-inch spindle lathes. Here you'll see a mist collection device, just a couple of 55-gallon barrels welded together, placed to clean parts off, blow parts off, and had an old mist collector from a machine tool on top of it. Just provided some cleanliness in the shop. Up in the top there, you'll see some of our CMM fixtures. Just pieces of block aluminum that were left over, we pulled out of the scrap barrel and machined into something useful. So anytime you can do this, you're both utilizing waste and providing a new means, a new technology for yourself. And so in conclusion, we can say that yes, change is inevitable. We've seen examples of that today, certainly. Take this with you. Exploration, observation, and questioning are the only means to gain any insight, and be sure you do that. Effective solutions can give us a competitive edge, right? Can set us apart from our competition. And I would note that it takes a company-wide effort, and ask yourselves, do you have that culture? So thank you, folks. I appreciate you staying with me today. Okay. Yeah. Should we take a look at some of the videos?
So your videos, are they pulled up online? Or where are they?
They're on the desktop.
Just these ones?
Yeah.
The computer resets.
Oh, really?
It changed itself to extent, it's just duplicate, so what you're seeing here was different.
Yeah. Here's a path that we use to control the flightings. Can we get that bigger? You can see the controller at work here. So what we did is we put the machine in machine lock, stopped it, and we could run on our graphics to see exactly what was happening with this radio milling process. Like I say, it was new to us. We didn't understand it necessarily And so the machine tool actually provided us a means here to do it. As far as I know, there's not much CAM software out there that can tolerate these kind of processes. Here it is actually being manufactured. You can see the sub spindle on the right-hand side traversing with the tool all in one motion. It'll get to the end of the bar, stop, reverse direction, offset the y-axis on the opposite side because we're cutting off center, and then work its way back. Climb milling both directions. So one guy offered up, well, why don't you just hold it rigid on both sides, right? And so you don't have a y-axis in the lower, just bring a steady rest up and support the center of it that way. I'll show you one issue we had there. This is the pulse generators in the spindles conflicting with each other and trying to auto-correct each other. And so you could put your hand on there and stop it, but what happened is we milled this part away, it became springy and was under torsion, right? And so that bar actually wanted to flex and grow in length as it tried to uncoil itself from the memory in the steel. So holding rigid on both sides certainly wasn't an option. You can imagine the chatter that we got with that thing acting the way it was. There you go. The last video I have for you here is the PLC project on the Tornos cam at work. Somewhat of an electrician's nightmare. I'm no electrician, but it worked. And here you see the sensors. What they're doing is they're measuring the reflective light from them. It can actually send that number out in analog if you want to, but we just used it as a simple I/O switch, on or off. Here you see it monitoring the cam ticks. Just a photo eye, counting them. Come around to the front of the machine. Here's the end working tools. Here's the trip dog for the tapping clutch. Trip right there, it's set and it came back. That's the correct orientation of it. And here you can see we're still trying to measure the drill. The Keon sensors are actually pretty neat stuff. They can compensate oil out of the picture. Is what they sold us anyway. I don't think they expected us to be actually putting it in a stream of oil. This was more for like assembly equipment and that would gradually build up oil or debris on them over time, where we were on and off with the oil, so that really wasn't an effective solution, but monitoring that trip dog certainly was. Again, I thank you folks. I hope you learned something today. Take something home with you, but be thinking innovation.
Nice job, Brian. Let's give him a big round of applause. Just again, a reminder that lunch is going to be served at noon, same place as yesterday. And it says here, let the group know that coffee pop will be after this Block 3 session in the area by the registration desk. If you would please, don't forget the evaluations. Again, we use these for future conferences, so thank you very much for your time. We'll see you at lunch.